Welcome to Math 31. This is a lesson showing additional trig identities, ones that are not covered in 30 pure, fairly simple ones, but ones that are typically developed using the sum difference identities. And I'm going to draw attention to a few of them, go through a couple simplification ones, and then give you the list of the ones that you will be expected to use in this course, in this unit. So to start, simplify pi plus theta. Now this is of form sine a plus b. And if you take a look at your formula sheet, you'll know that this is equal to sine a cos b plus cos a sine b. So if we were to expand the one we were given, pi plus theta, we would get sine pi cos theta plus cos pi sine theta. Therefore, when we simplify, the sine of pi, sine of 180 degrees, if you take a look at your unit circle, or use your calculator, you'll get 0 times cos theta. And then cos of pi is negative 1, and then negative 1 times sine theta. So really, the sine of pi plus theta is equal to negative sine theta. This is an identity. So it would mean if you did graph these on your calculator, I didn't bother myself, but if you did enter, say, sine pi plus x, and y2 is equal to negative sine x, and then if you were in rad mode, and then zoom 7 is a nice touch to align your axes and set your window settings for conventional trig graphs, you should get the same graph, which means that it is an identity. Okay, then the next one, cos of pi over 2 minus theta. Well, this is a form cosine a minus b. Cosine a minus b is equal to cos a cos b plus sine a sine b. So in this case, the cosine of pi over 2 minus theta is equal to cosine of pi over 2 cosine theta plus sine pi over 2 sine theta. Cosine pi over 2, well, that is also equal to 0. So we get 0 times cos theta. Sine of pi over 2 is 1, and then times sine theta. So therefore, the cosine of pi over 2 minus theta is equal to sine theta. So easy to check by graphing as well. So another identity. And now you notice these two ones I looked at were both giving you quadrantals. So you had pi over 2 and you had pi. And 3 pi over 2 would have produced similar results. Quadrantals they lend themselves to this sort of identity because the sine and the cosine value of those angles will either be 0 or 1 or negative 1. And so that means that you typically can get a simplified version of it. And those of you who remember their trig will recall that the graphs, transforming the graphs, that when you do put these phase shifts on, then a wave can be put in phase with another wave. So if we were then to look and classify these identities, first off what they call the complementary identities. Complementary identities are because angles that are complementary will add up to 90 degrees, so pi over 2. So happens that the cosine of pi over 2 minus theta is equal to sine theta. We have just demonstrated that. As well, the sine of pi over 2 minus theta is equal to cos theta 2. Interesting. And then the cofunction identities. These ones would go like this, typically. Sine of pi minus theta is equal to sine theta. Sine of pi plus theta is equal to negative sine theta. So we went through that one. Cosine of pi minus theta is negative cos theta. And cosine of pi plus theta is equal to negative cos theta. Now, there's other versions of these. I'm not bothering with the 3 pi over 2 ones, obviously, or as well, I'm not doing like some of the other ones like pi over 2 plus theta. So we have all these things we could do with them, and I'm sticking with these. These are on your formula sheet, so keep the formula sheet in front of you and use these. If you ever need other ones, say, for example, the cosine of 3 pi over 2 minus theta, then you'll have to derive it yourself using the sum difference formulas, and it's not the end of the world if that happens. Shouldn't, though. Mostly I'll concentrate on these. There's also tan ones. And in most textbooks, they do actually identify those tan ones, but tan is also a combination of these. So tan is equal to sine over cos. So you could turn any tan complementary or cofunction identity into a tan one simply by going sine of that argument over the cos of that argument. Now, the other ones are the symmetry identities. We use these quite a bit. Sine of negative theta is equal to negative sine theta. And the cosine of negative theta is equal to cosine theta. So this means that this is an even function for cosine. And it means that this is an odd function for sine. We use all of these quite a bit. And they show up when we do limits, principally, but also derivatives. When we're taking something that's in an unmanageable form, and through these identities, through identities in general, we can put them into a manageable form. Now I am going to draw these ones out so we can take a look at them just regarding this odd-even issue. Y is equal to sine x. If we take a good look at this, you can see that it is going to be odd. It makes sense. So for example, if you took this point right there, which is pi over 2, comma 1, that point is on the curve, but so is negative pi over 2, negative 1. And that's what you would expect from an odd graph. If it's reflected in the the origin, it means that it has undergone reflections over both axes. Same thing then with cosine. If you look at that, this one is perfectly symmetric about the y-axis, so you can see that any point that you would care to pick, say pi over 2, 0, well, on the other one you're going to have negative pi over 2, comma 0. So that's how these go. Now, to simplify a few using specifically the symmetry identities. Now, this next batch of questions is optional to approach it this way. In fact, I would say that most of you wouldn't bother doing this if you were, a real world type application. But it is interesting, and it's a bit of practice with the symmetry ones as well. So if you had cosine of negative 7 pi over 6, now that you can evaluate by just taking the angle, finding the location in quadrant 2, getting the reference angle, etc. like that. We've actually done almost the identical questions. But I'm going to use the fact that the cosine of negative theta is equal to cosine of theta. So therefore, this is equal to the cosine of positive 7 pi over 6. And then if we were to solve that, you would recall that this 7 pi over 6 is in quadrant 3, and it's a reference angle of pi over 6. So you've got your unit circles. Keep them around, because what we want is the cosine of pi over 6 in quadrant 3. And your unit circles and those triangles will tell you that the ratio is equal to root 3 over 2. So this is equal to square root 3 over 2. And then you've got to ask yourself, in quadrant 3, what's the sign? Well, it is negative. So we do it like that. Now, it's not necessary, but it does work. If you put this through your calculator, of course, you'd get negative 0.8660, which is the same thing. Second one, kind of a similar thing. The sine of negative 2 pi over 3, if you remember that the sine of negative theta is equal to negative sine theta, then this one turns into negative sine 2 pi over 3. And that being the case, the sine of 2 pi over 3, well, I'll do the same thing. You probably don't need to draw this. Look at your unit circle. 2 pi over 3 is there. This really is the sine of pi over 3 in quadrant 2. And the sine of pi over 3 is root 3 over 2. Now the fact that it's in quadrant 2 means it's positive, but then when we apply the negative, we get negative root 3 over 2 as well. Now the last one of this sort is interesting because it's a reciprocal function. Now this can be approached a number of ways, but you might be thinking this is 1 over sine of negative 5 pi over 4, which is negative 5 pi over 4, if you could read that. I barely can. So this really turns out to be 1 over negative sine of 5 pi over 4. So using that sine symmetry identity, we can do that. So 5 pi over 4 takes us into quadrant 3, deep into quadrant 3, and we really want the sine of pi over 4 in quadrant 3. And the sine of pi over 4, depending on how you want to write this, is root 2 over 2, or 1 over root 2, but you're negative because you're in quadrant 3. So this becomes 1 over negative root 2 over 2. So that becomes positive, and then when you take the reciprocal of it, you will get 2 over root 2. So the one way to approach a problem with that. Don't know if it's the best. I think in a lot of cases it's easier. In fact, in most cases, it's easier just to take the negative angle and take it to wherever it takes you, or go wherever it takes you. But this is a possibility. Now this is more like it. A fairly messy looking expression. You're asked to simplify. In actual fact, it's proof. What I'm going to do with this one is using the symmetry and the complementary and cofunction identities, I'm going to break this left side down, this dirty side, until it's equal to the clean side. And the fact is, secant of negative x is equal to 1 over the cosine of negative x. And 1 over cosine negative x, according to what we know about symmetry properties of trig functions, that's equal to 1 over cos x. It's even. And then sine of pi over 2 minus x, take a look at your cofunction, or your complementary identities, and the sine of pi over 2 minus x is equal to just plain cos x. And then sine of negative x, according to what we know, is negative sine x. We can take the negative out of the argument and bring it outside the function. And then the cosine of pi over 2 minus x is equal to, the cosine is equal to sine x. So putting this whole thing together, 1 over cos times cos is 1. And then minus sine x times sine x is sine squared x. And 1 minus sine squared x is equal to cos squared x, which is exactly what we want. So cos squared x is equal to cos squared x, QED. So we did it. So those are some of the extra identities that you need to be familiar with so that you can tackle most of the problems. The next lesson will be a bit of a review on trig identities, a 30 pure topic, but going a little deeper into it as well. Thank you for your time.